Yeah, let's go. Let's quick review of what we have done in the last classes. The communication channel through band limited channels. So absolutely is very simple. I told you that band limited channels. Okay, exactly the band limited channel, because whatever the kind of the channel you are going to use, that channel is limited for the certain frequency. That means that allows the frequency of certain, allows the certain frequency of the signal, because it itself is a limited to the bandwidth. As simple as this analogy of the band limited channel can be modeled, can be think as a linear filter. What exactly the linear filter? Linear filter is the one, a linear filter, filter is the one, okay, exactly. Linear filter is the one which passes the desired signals. So as simple as that, the analogy of the band limited channel, which is also same, which works same as the band limited the band limited filters. So we can thought we can understand the behavior model working with of the band limited channel from the working of the linear filter. That is exactly we call it as communication through band limited channel. It's very clear. So how, let's go back, how exactly band limited channel sorry, linear filter works. As simple as the linear filter has been designed to pass certain frequencies. That is what we call a desired frequency. Whatever the signal comes, let us be analog signals, let me say that each divide, that signal will be divided to infinite sample frequency. Then each signal will be passed on to the filters. That filter will convert the desired frequency of the infinite samples frequency as a unit impulse response, and add the summation of all the unit impulse response of the infinite sample frequency response, and it will give the total response of this filter for the desired frequency. In a similar manner, we can thought also band limited channel. What will happen? Will send the will transmit the signal of the same frequency, of the frequency which is equal to its bandwidth, and divide that signal into what exactly? We can divide the signal into infinite sample frequency. The response of the channel to each infinite sample frequency can be taken as a unit impulse response of the bandwidth channel. Likewise, each infinite sum of the transmitting signal can be taken as an impulse response of the channel, and we can construct the response of the band limited channel at the output. Okay, as simple as I explained you already that. So look back, this is, see, look back, CF is for a linear filter, you know that CF is equal to CF is equal to what? The response of the linear filter, which is equal to minus into the plus infinity CT. Exactly, the CT is equal to what exactly? This is impulse responses e to the power of j 2 pi is equal to the frequency frequency of the infinite sample and frequency. So since we equate this is the response of the band linear filter, we have equated this into what exactly? Band limited responses also. So that means C of f, the response of the band limited of is equal to C of f is equal to integral of minus into the plus infinity C of t is equal to unit impulse response of the channel into the e to the power of j. This is exactly the frequency response of the band limited. Very important, please mark it. How we got it? Whatever the transmitting message signals will absolutely convert into the infinite simul frequencies. Exactly, infinite simul frequencies, infinite simul. Each infinite simul taken as the response of the channel, and construct each response of the magnetic signal into that. That is what exactly minus into the plus infinity. So now exactly we have gone through what you call it as we have gone through how exactly the linear filter model. So once you assume that band limited channel, we have gone through linear filter model for the band limited channel. As I told you, this is very simple. See, this is the input G prefix T cap of T is equal to the signal to be transmitted, and who's the frequency response by taking the frequency, by taking the Fourier transform of GT of T into this, we'll get back a response, frequency response in that. As you assume, this is a linear, this is a channel, this is absolutely working as a linear filter. See, let us, I told you that CT is equal to a unit impulse response of the filter, that is a channel, that is a filter, absolutely. So this is a frequency response. See, now exactly H of T is equal to the response of the channel, exactly response of the channel. How exactly response of the channel for a CF, G will be exactly G prefix T will be move across by in a tau scale, as simple as convolution integral. Taking the convolution property, that is convolution property, or summing interval or running interval of the convolution integral, we can just pass the signal over a tau scale along with the frequency signal. We'll get back to h of t, that is total response, by integrating minus infinity to the plus infinity. So during, very clearly that during this transmit of the channel, there is something noise will be absolutely will be included it, and I said that is exactly called as n of t. Therefore the total output of r of t is equal to h of t is equal to n of t. Please mind it here very clearly, as this is the output of the channel. Here this is exactly the receiver. This r of t will be the input of the receiver. Okay, exactly. That means this is the input to the demodule. As you know that demodule is the first block absolutely at the receiver. This look back, this r of t will be what exactly is, it takes the only the desired frequency of the transmitter. That means the demodulator will have a filter, what we call as a match filter, which is according to the what exactly the channel. That is exactly we call as a match filter. Please mind it. This is the input to the demodulator. Demodulator itself is a match filter, because match filter means the frequency of this will be matched with the frequency of this. That means that whatever the frequency of the RF will allow the frequency of this. Okay, that is exactly this. But R of t will consist of h of t, n of t. Okay, exactly. This is I mentioned. This is I told you that this is the response by convolution integral. Just taking this. Okay, I mentioned it. So that is our frequency response of. Look back, the frequency response, that is h of t, is equal to taking by the Fourier transform. Small h of t is equal to gt of f is equal to c of f. The frequency domain g of f opens the spectrum. That what the frequency now gives the frequency spectrum of a signal g prefix t of the, that is it gives the magnitude of g prefix t of f. Okay, exactly. So this is absolutely, therefore the channel alters that means, see, if you send, if the band limited channel is ideal, that should be whatever the output response has to be the output response, the output response, that is output response has to be the just frequency response of the signal after passing through that. But here look back here, this is the frequency of the signal, but it also contains a CF. That means that instead of, in ideal case, we do expect h of f is equal to what, g2 f of g prefix t. But what really is happening is that g prefix t, instead of that, it is also contained c of f. That means that what after the that means that the signal transmitting signal will alter and distort the signal. So r of t is equal to h of t is equal to n of t, exactly output signal of the band limited channel. This is absolutely mentioned. So this means you're taking the, I told you that in the receiver, this is the exactly g or f is equal to h of f e to the power of minus j25 f of t. This is the response of the match filter at the receiver. This is absolute r of t is equal to the input to the receiver. The input to the receiver is the first block in the receiver is a demodulator. This demodulator is absolutely a match filter. Before taking demodulator, what will happen? There is exactly the match filter. In that match filter just matches the frequency of the transmitted signal with the matching frequency of the transmitter. That's why we call it a match filter. And we have the response G prefix RFF is equal to what exactly? The receiver of the information. So therefore, output of this is absolutely this. So that means clearly mentioned. And these are the exactly, this is absolutely we derived, because whatever the signal is passing through the channel is equal to power per spectral density into what exactly the frequency response. This is exactly the power spectral density of the what? A channel. The output of the match filter has to be the same as the output of the channel, and hence the whatever the spectral density of the match filter is equal to the what is spectral density of this. That is exactly yes, n of f is equal to what? N by 2 into h of square. Okay, by AWGM theory, the variance of this channel is depends upon the what exactly noise. The variance of the noise power at the match filter is equal to what exact integral minus s on f. This is the variance. The mean is mean of the signal passing to the channel at any point in the channel. It's only depend upon the signal but not on the noise. Where exactly the variance of the signal passing through the channel is always depends upon the noise but not on the signal. That is why this is exactly we consider. Therefore, when you take the signal to noise ratio, we have to take these two factors of this. So therefore, the signal noise ratio has been given by has been in accordance with the equation of the matched filter. Okay, see, this is Okay, exactly. Now let's come back. This is digital PAM transmission to the band limited post model. Yeah, exactly. The basically what we want to transfer the signal within in terms of the digital signal. But you please mind it in a modulation technique, whether BFSK or FSK, we are going to use the exactly the signal in the form of analog signal. Even that means that we are protecting the binary sequence pulse. That is itself in the form of the information code. That is binary input sequence 100. That 100 will absolutely put into the binary sequence. Binary sequence will put into what exactly the carrier wave according to the modulation, whether it may be PSK or FSK. That is absolutely the output you are going to transfer. The signal we are going to analog form. But generally in the digital, if you look back in the digital way, we have to transfer with exactly what a discrete signal, because to possess some kind of an advanced line similarity and other factors, as we discussed in the earlier chapters. So what will happen here? That means that we need to convert that output. That is exactly through how you going to convert the analog carrier signal which contain information into digital through a process called as what we call it as PAM, that is pulse amplitude modulation. Look back at the input sequence here, 100001. This 100 input will be converted into what exactly binary sequence pulses. These binary sequence pulses will be converted into what a carrier base in exactly the transmitting filter content. The transmitting filter will pass the information. Now in the transmitting filter, we divide this into what exactly into digital through help of the what exactly pulse amplitude modulation techniques. How you are going to divide? We just divide taking the generally we divide this into by sampling theory, so that can be taken out because EAN is exactly coefficient of each sampling, and G of T, this is the information exactly we're passing T minus N of TS. Okay, so that means based on this is at this point we are dividing the G of T that is exactly contained in the carrier wave along with the divide taking the sample at every as per the sampling theory at every sampling rate, let us say N2. This is G of T, just taking the sample at every T of G of T has been moved across the N of T, will get back the samples. So similarly, then this is the input to the channel, that is a digital signal with PAM through PAM pulse digital modulation techniques. Exactly this goes to here. The after channel, the R of T will be considered of the R of T, as you know that H of T plus N of T. H of T is a response, the response of the channel. So that means R of T should consist of an impulse response of this plus what we call noise N of T. This will look back a noise N of T. So R of T, this is exactly T of N minus 2 is equal to response of the pulse as a response of the response of the channel as an impulse response. This is absolutely is given here. So that means H of T, that is the response. C of T into G of T into what exactly into N of T. Okay, exactly. This is the signal. So that means output of this is there. So when you take in that what you call this is the output, this is the input of the channel. As I mentioned, how the response goes. Okay, simple aspect. So this is the output of the remaining. This is exactly when you take in the output in a time domain of Y of T is equal to just like a convolution sum as summation in minus input to the plus of this A into X of 1 minus T minus into WN. Just taking that X of T is equal to that is output of that, the output signal. Absolutely, it is H of T with exactly what GR of T, very mentioned, because here output of the match filter is equal to the output of the channel. Absolutely, you mention it. That's why H of T, the response of the channel, multiplying to the what exactly the frequency response of the match filter is exactly here. This is match filter, which take the response of the frequency within the out of the frequency will be out and out. So G of T, that means exactly here H of T is equal to what G of T into C of T into GR of T, the output of the response. So therefore, this is just mentioned. X is equal to output signal, output response. This is the output signal. Output signal again we are going to take it out exactly into sampling response again. That is a very important after taking the sample, because whatever the signals comes through, that sampling we are going to take and check that whether within that. Okay, this is absolutely mentioned here. So this is just changing into X of N minus T is the sampling period. M is equal to range is the variance. Okay, this is MT is equal to sample of at every for M of T. There is a exactly for there is a noise signal, so that we can convert into a very simple factor. Y of M is equal to summation N minus to the AN into X of N minus plus omega M. Just substituting back to this, just rearranging this factor, we'll get back, because look back, X of is here, X of 0, this is infinity, then X of 0 is the value at which you are going to get the values. That is why we have taken the X of 0 value. X of 0 value is the value of real terms, where exactly this term is this term exactly this terms is or multiplied by the sum of the signals, because just due to the inter-symbol interference and noise signals. Okay, the first term in the right hand side. So when you take the output of the response is equal to what exactly? We'll get back to h of response of the minus into the plus t square of t into what? Minus into h square of this. We'll get back to this equation. So you're just looking back this equation, h square of t, then the response of the output signal, response of the this time domain. We need to convert in a frequency domain. I will get back to it. I hope I explained every whole chapter number 4 is very clearly. And again, in fact, so that, okay. So now let's go back, what we call it as signal design of the band limited channel. See, look back, as mentioned that h of the frequency response is equal to the frequency response of the channel will be multiplied. See, instead when you send a something signal, okay, exactly, when you send a something signal, g prefix t of t, so we do expect the response of the channel. That means once passing to the signal, how it is the response, I just mentioned it, as simple as that, taking the convolution, integral convolution sum the response. That's simply we're taking unit impulse response by invoking the convolution power property. We just moving what I call g prefix t along the tau scale with the c of f. We'll get back to convolution integral. That is exactly I mentioned it, h of t is equal to y. So that means here, if you pass the signal g of t, we should get at the output g what I call only the response, that is the response, that is the frequency magnitude of the input signal, that is absolutely g of f is equal to what? Capital G of t of f, where we have a term called as c of f. C of f is equal to what exactly? This means impulse. That means ideally we do h of f, the frequency response of the channel is equal to g prefix of t, but we do expect of this or cf. So that means signal design, that means we need to avoid this, what I call it as, we need to avoid this kind of a transmission receiver signals. Okay, exactly. So what is exactly here? So you look back here, very simple. This is exactly, this is the signal. The C of F is equal to, I define you, C of F is equal to the frequency response of the channel. The frequency response of the channel is exactly given C naught into e to the power of j 2 pi f naught here. C naught j 2 pi f naught here. Okay, exactly. So you look back here, this is the very limited, very basic presumption that we are going to pass the signal, is we're going to pass the signal, or in other words, the bandwidth channel will accept only the frequency desired for it. Absolutely, it means that desired for it, absolutely it means that, okay, exactly, absolutely it means that it will only accept the free bandwidth of it, and remaining signal of the property is rejected. So C of S is equal to given by C is equal to C. Look back how the construction goes. Simple, please understand, very simple here. Whatever the signal comes to the channel, we are just split that into infinite simultaneous frequency. Each will have a something frequency that is e to the power of j 2 pi, and each one will be passed through the build. Each one will pass through the channel, and it will take the response of the impulse response of the each infinite simul, and take the, likewise we can construct the magnitude of the signal. Therefore, according to what we assume, the presumption of that, C naught is equal to e to the power of j minus 2 pi f of t naught. Okay, this is exactly the signal. So this signal has to be less than or equal to w, that is w is equal to bandwidth of the channel. The signal whatever passing to the channel will be signal frequency should be less than the width. That is why this, whatever the impulse response you are going to take should be within this width. Otherwise, if the frequency of the signal transmitting is greater than the bandwidth of the channel, absolutely, so this magnitude has to be 0. This is exactly we have mentioned it. See, this is very simple. Now the basic thing is what we are looking, we have to design the signal such a way that it passes through the band limited channel, that is within the frequency, and also should not get involvement of the what I call it as involvement of any other kind of frequency. It has to give only the pure response of the input signal, that is small g of t, or at the output you should get capital G t of t. But as you mentioned it, at the end of the day, at the end of the band limited channel, we are going to get the what exactly g of t along g of t aligned with the convolution of what I call C of f, as we mentioned that. So that C of f will be absolutely what exactly a noise due to the additive noise, maybe a noise due to the channel, plus of course and that additive noise is equal to n of t. Okay, so this is exactly how do you how do you exactly get only the frequency term other than the what exactly some other terms contained in the output? As you mentioned in the last class, last discussion, last 5-minute discussion, I told you that the output of the channel will contain first of the desired frequency, then it will contain what exactly the factor is absolutely called as ISI, inter symbol interference. That means the real signal, that is a signal intended, will get multiplied to some of the noise signal, will call it as inter symbol interference, along plus some of the noise, additive noise of the channels. Okay, see that basically what we do is output of the channel. If you take y of t is equal to x of x on x of 0 is equal to real output plus a into summation, as I mentioned in that is exactly the interference. Third is what exactly omega t. So that is omega t. So wt is equal to what you call it as not a omega t, please, sorry. Wt is equal to what? Additive noise of the signals. Okay, so that means this is exactly we do expect. Okay, but in we do expect, in generally we do see h of t is equal to, in generally we do expect the receiver, as I mentioned that this is the receiver of that. And basically I told you that there is an immediate filter at the output of the channel, so immediate of the filter will take the response. That means this we do expect this is equal to this. Okay, the match filter response has to be to the match filter, what we call response of the band limited channel, that is d prefix t of t of this. And when you this, but when the last look back here, the output of the channel is in the digital signal can be taken as a sample output of response of the channel for a given. So you look back here, I mentioned it, this is exactly the desired, this is exactly what ISI term, then this is exactly additive noise. So that means output of the band layer contain 3 terms, but we desired only to expect of this is due to the what exactly some of the signal get interfered the symbol transform. This is exactly the noise. Okay, basically what we expect in reality, we do expect only this y of m of t is equal to x of 0 is equal to what this output one, but we do expect, we do get of this, but we as a successful engineer we need to crash this, we need to remove this factor from the output so that I'll get a genuine output as possible as. So that is getting designing of the signal to get of this only this, we call it as a signal. Exactly, look back here, we call it as signal design for band limited channel. How exactly it goes, that is exactly different. So simple aspect is that, look back here, so this is the real output. So look back here, we have trend, see the output signal. Okay, exactly, there's a, so you look back here, the equation phi and b, that is what I shown, gives the output signal for a band limited channel, from which you can calculate, we can conclude that margin of additive noise, that is I mentioned, the third chop additive noise error, that is exactly the term ISI test of the positive. So therefore, how exactly, if you keep y of t is equal to plus desired frequency plus ISI plus additive noise, when you draw this, when you taken the output of the channel along with that, we can see the output response. We call it as I pattern because we are going to see that it has been done in the textbook point of view. That is what we call as I pattern. This is I pattern of binary pause of this signal. I pattern of the quarter. This is for m is equal to 4. That means absolutely we're sending 4 signals. So how exactly appears? Look back. These all interference is called as exactly ISI. Some of the insights. See, look back when you say there is an this exactly there is an inter. This when you say take the 2 signals in the output of the signal. Okay, exactly here. Okay, exactly. This is absolutely mentioned in I pattern of the binary, this things, I pattern of coordination. And look back how the signal, see, we do expect that this is exactly the signal, but interference with this aspect. Okay, exactly. These are the, just see the very important model you should understand. See, this is exactly we require of the, this is what if output of the consign is absolutely output is contained this part. This is the real design. This is what ISI. This is what non-additive noise. We'll get back to these 2 forms. Okay, exactly. This This is the sensitivity part, and you can see these are the signal how exactly disturbs. Okay, so right. So now this is the, now how do you, that is exactly we need to consider, that is absolutely okay, exactly. Right. Uh, Yeah, now let's go back. Band limited, design of a band limited. See, design of a band limited. Okay, exactly. Design of the band limited. Okay, design of the band limited. Design of band limited for zero IC. How exactly? Basically, what y of t is equal to, I mentioned it. Y of t will consist of three terms. The first is desired frequency. Second is exactly what we call it as the zero ISI. That is exactly inter-symbol interface. Third is additive noise. Additive noise is quite disturbed. Okay, quite very small, but very problematic is that you can see the last quadrature for m is equal to, for a four binary pulse when it exactly falls, what will happen? The output signal is get distorted. That exactly what we mentioned quadrature. Okay, exactly here. So we know how to avoid that. How to avoid the zero ISI? That is absolutely called as the design of a band limited signal for a zero ISI, which is exactly called as the Nyquist criteria. So what is exactly, as you already know, this is the G of, this is capital G of T, that is prefix T of T, that is exactly input data transmitted. This is exactly the channel. This is exactly the channel goes here. The output response H of T is equal to this, N of T is equal to noise additive. We'll get back to the receiver. So what we'll get back to transmitting form. As I told you, this is exactly the transmitting form, exactly the transmitting form of this is, and as I know, this is the input. That means channel will have response. This is h of t is equal to response. A response is equal to unit impulse response, that is of the each infinite sample of the input frequency channel. This is additive noise. Exactly, we'll get back. This is all I explained already. Look back how, what is exactly this. So look back, this is exactly output. I mentioned it. Y of t is equal to y of mt is equal to, this is desired, this is ISI, this is additive noise, exactly here. Okay, right? X of, so when you take the frequency response of this, we'll get back to what G of T F, C of F, G R F. This is exactly the how the output response of the match filter, that is output response of the what exactly the channel of this. So this is exactly. So let us see, look back, see here. That means this is the term. This is the term, absolutely the big problem for us. Okay, because it creates the noise. If there is something noise inside it due to additive noise, let's, even though we have mentioned it exactly what, even though we mentioned it CF is equal to unit impulse responses of this, but due to some of the aspect, there is a content, the impulse response will contain some of the what we call noise signal here. So GT of F, C of F is equal to GRF. This is the information, this is the total expected output, because the channel of the output is equal to this much. Okay, so for a kind reference, let us assume C naught, that is the C naught value is equal to 1. T naught is equal to what we mentioned, finite delay, and TMT is equal to sampling period, where this is exactly, this is M of T is equal to sampling period, which is the sampling period for the output signal. So what will happen here? So look back. So we wanted to cancel this, look back, very important. Just I wanted to cancel this. What is exactly, look back here, x of m minus n. X of m minus n means what we call x of mt is equal to nt. X of mt is equal to nt. That means sample of m is equal to sample of n always. In such situation, what will happen? This term becomes zero and whole this stick becomes zero. Basically what we are interested, what we have seen this, even the output of the channel, band limited channel, gives the desired along with interference, the output we does not like where what we expected. Okay, so that means absolutely here. So that means we need to cancel. Look back, a of here, x of x prefix m minus 1, x prefix m minus 1 is equal to what? X of mt minus nt. X of mt minus exactly ent. That means if you make this zero, this is possible if you make, look back here, so you look back, x of nt. So x of nt is equal to 1 when n is equal to 0. That means when wherever the 0 comes, the output is there. That means if you make x of mt minus nt, x of mt minus nt, is equal to 0, automatically the output equation of the band channel will become 0, because y of t absolutely consists of the desired frequency plus along with that, okay, plus along with the what I call it, along with the ISI and additive noise. So that x of mt minus nt, when I make how exactly n of t, the sampling is equal to m of t. That means m of t is equal to when you you make this 0, if you make n is equal to 0, x of m of t minus n of t, that is x m of t minus n of t is equal to 0, we'll get back to x of m of t. That both this is actually in order to get the desired output frequency, okay, by avoiding of that is x of, okay, x of n of t minus m of t. So when you make n is equal to 0, that means absolutely we get back to x of m of t minus n of t is equal to x of m of t minus n of t, that is x of m of t minus 0. We'll get back to what exactly, x m of t only. Therefore, so in order to that, therefore what we can say, so look back, the second term of ISC can be removed if the second term is 0, which is possible if and if only x of m of t minus n of t is equal to 0 for n is equal to m x of 0. So that means we can make it this is 1 when n is equal to 0, or otherwise it becomes 0 for other. That means the x of n of t, that's output signal sampling, which you are going to take exactly x of n of t is equal to 1 is equal to n of 1 is equal to when n is equal to 0, and 0 for most of the things. So if you design the necessary sufficient condition for x of f, that is a frequency response to the bandwidth channel, that is a frequency response to the match filter, which is also same, or x of t, this is absolutely the output signal, that is output signal to remove x of the sampling of the output of the bandwidth channel should be 1 only when is equal to 0, where it has to be 0 in other. Such we call it as what I call a Nyquist pulse shaping criteria or Nyquist condition for 0 eyes. So what is exactly the Nyquist criteria for Medal? The necessary and sufficient condition for x of t are simply x of n of t is equal to n minus 0, n is equal to 0, n of this, okay, n is 1 is equal to n of 0, and 0 n does not is equal to 0, okay, right? The, so this is exactly, this is x of t, this is the Fourier transform x of t. So if the Fourier transform of the x of t is equal to, given by this is equal to x of the x of f of plus n by 2 is equal to t. So that means exactly the frequency response, absolutely the frequency response is equal to of the channel fw of this, okay. So next, let's continue. Next week, next class, sorry, tomorrow class, I'm going to continue design of band limited signals with control ISC, partial response of the signal. This is also very important, and that I can complete by probably tomorrow. Tomorrow we'll conclude this, the fourth. Okay, thank you.